Hi, welcome to my video in ML from Scratch series. Today I want to introduce you to random processes, and in particularly the Gaussian process. In the next few minutes we'll derive the Gaussian process regression and implement it from scratch in Python. GP regression is widely used in applications that require uncertainty measurements, and I'm really excited to share these concepts with you. Let's get started. Let's start off with a quick overview of random processes. We'll then define Gaussian random process mathematically and derive GP regression algorithm from first principles. We'll conclude with from scratch implementation of Gaussian process regression in Python. Random processes focus on a sequence of random variables. This sequence is denoted below as x1, x2, and so on, where each xi is a random variable. Successive samples in a random sequence will in general be correlated as measured by the covariance function. Some examples of random processes include Bernoulli process, Poisson process, Gaussian process, and others. In this video, we'll focus on the Gaussian process. Suppose we have a function f that we're trying to learn from input data x and output data y. In other words, we are trying to learn function f where y is equal to f of x. In Gaussian process, we're interested in computing a distribution over functions, or p of f given x and y. A Gaussian process defines a prior over functions that can be converted to a posterior once we have seen some data. To define a distribution over a function, we only need to define it over a finite number of points, x1 through xn. And a Gaussian process assumes that the probability p of f of x1 f of xn is jointly Gaussian with some mean and covariance. Now that we have a better idea what we're looking for in a Gaussian process, how do we compute this posterior over functions? Our goal is to make predictions on new inputs. Let's denote this new point as x plus and the function output as f plus. Then we can write down the joint Gaussian distribution between the training point x and the new points x plus as follows, where k is our covariance kernel function. We want to solve for the posterior. To compute it, we can apply the standard rules for conditioning Gaussians as we'll see on the next slide. Applying the rules for conditioning Gaussians, we get the following update formula for the Gaussian process regression. Let's take a look at the pseudocode for Gaussian process regression. We define a radial basis kernel function and then we compute the posterior based on the expression we obtained on the previous slide. Note, due to the matrix inverse, the computational complexity is order n cubed. Let's take a look at the Python notebook. Feel free to read through the theory once again at your own pace. The notebook is linked in the video description below. I'm going to go straight to the code. We start by importing numpy, matplotlib, distance function, and fixing the seed for reproducible results. We define a GP regression class, and in the constructor we take in the training data x and y and our new to be predicted data x test, and initialize our mean and covariance functions that are defined below. We assume zero mean Gaussian and radial basis kernel covariance function. Then we compute the ingredients of the posterior, compute the matrix inverse, and compute the final posterior values from mu and sigma. Finally, we have functions for generating plots and sampling from multivariate Gaussian. Notice that in the plot function, we're filling in 2 standard deviations from the mean around our sample points. Next, let's generate some sample training and test data. In the next cell, we're going to draw 3 samples from Gaussian process prior distribution. You could see the 3 samples drawn from the prior. Next, we're going to compute the posterior distribution and draw 3 samples again, but now from the GP posterior. You can see the variance is low around our training data, and in between we have some uncertainty as measured by the Gaussian process. And we're done. I hope you have a better understanding of Gaussian processes and will be able to use them in your application that require uncertainty measurements like Bayesian optimization. Thank you for watching. I hope you enjoyed this video. If you're interested in more educational ML content, please hit like and subscribe to my channel. Looking forward to seeing you soon.